There's something haunting about the vast stretches of the cosmos we simply cannot reach. Picture a universe so immense that even our most advanced technology, our boldest imaginations, can't bridge the gap to its most mysterious corners. These are places where the laws of physics as we know them twist into riddles, where light itself seems to vanish, and where the very fabric of space and time behaves in ways that defy explanation. Welcome to the enigmatic regions of the universe, the uncharted territories that stir our curiosity and remind us just how much we have yet to discover. Think about the last time you stood beneath a clear night sky staring up at the stars. It's humbling, isn't it? That glittering expanse is just a tiny glimpse of what's out there. Beyond the familiar constellations lie realms so strange, so utterly alien, that they might as well be from another dimension. Black holes that warp reality, cosmic voids so empty they stretch for hundreds of millions of light years, and mysterious dark matter that binds the universe together yet remains completely invisible to us. These aren't just distant curiosities, they're the frontiers of human knowledge, the puzzles that keep astronomers and physicists awake at night, searching for answers. And that's where our journey begins, because hidden among the stars are 25 of the most baffling, awe-inspiring regions in existence, places we can observe but never truly explore, at least not yet. Some are locked behind insurmountable distances, others by the sheer fury of cosmic forces that would tear apart anything daring enough to approach. But their mysteries beckon us, whispering questions about the nature of reality itself. What secrets lie within these forbidden zones? What would we find if we could cross that impossible threshold? Strap in, because we're about to embark on a voyage through the great cosmic unknown, unraveling the enigmas that challenge everything we think we know about the universe. The adventure starts now. The Great Attractor lurks in the cosmic shadows like a phantom, tugging entire galaxies toward it with an invisible hand. Nestled around 250 million light-years away in the direction of the constellations Centaurus and Hydra, this gravitational enigma defies easy explanation. Imagine the universe as a vast river, and thousands of galaxies, including our own Milky Way, are caught in its current, drifting helplessly towards something we can't even see. That's the power of the Great Attractor, but here's the catch. Our view of it is blocked by the thick disk of stars, gas, and dust that make up the plane of our galaxy. It's like trying to peer through a dense fog, where the very thing hiding the answer is also pulling us toward it. Scientists first noticed this cosmic tug of war in the 1970s, when they mapped the motions of galaxies and realized they were all streaming toward the same invisible point. The sheer scale of the force required suggested something colossal, perhaps a cluster of galaxies with a combined mass tens of thousands of times greater than the Milky Way. Yet, even when they pointed telescopes in that direction, they found only scattered galaxies, nothing dense enough to explain the pull. That's when the theories began. Some suggest it might be the heart of an unimaginably massive supercluster, a knot of dark matter and galaxies so dense it warps the fabric of space around it. Others speculate it could be a rare manifestation of dark energy, the mysterious force accelerating the expansion of the universe, acting in reverse here like a cosmic vacuum. Then there's the strangest possibility of all. What if the Great Attractor isn't the final destination? Recent observations hint that this gravitational powerhouse might itself be moving, pulled toward something even larger and more distant, known as the Shapley supercluster. It's a cosmic matryoshka doll of mysteries, where each layer reveals another question. For now, the Great Attractor remains hidden in plain sight, a reminder that even in an age of space telescopes and advanced astronomy, the universe still keeps its deepest secrets just out of reach. One day, with new technology or sheer persistence, we might finally lift the veil, and what we find could rewrite our understanding of gravity itself. Now picture a cosmic desert so vast it could swallow thousands of galaxies without a trace. That's the Boötes Void, a staggering emptiness stretching 330 million light-years across, where the usual glitter of stars and galaxies gives way to almost nothing. If you were to fly through it at the speed of light, you'd traverse distances that dwarf our entire local group of galaxies and still encounter barely a handful of celestial neighbors. It's so conspicuously empty that when astronomers first mapped it in the 1980s, they double-checked their instruments, convinced there had to be a mistake. This gaping hole in the cosmos defies everything we know about how the universe organizes itself. After the Big Bang, matter clumped together over billions of years, weaving the intricate web of galaxy clusters and filaments we see today. But the Boötes Void is a glaring exception, a place where that cosmic scaffolding seems to have collapsed. Only 60 or so galaxies have been spotted in this immense void, a number so low it's like finding a few scattered grains of sand in an Olympic-sized swimming pool. The handful of galaxies that do reside there are eerily isolated, drifting like lone ships in an endless ocean of darkness. So how did this void come to be? One theory suggests it's the ghostly imprint of an ancient cosmic battle where smaller voids merged over eons, leaving behind this colossal emptiness. Another idea points to dark energy, the mysterious force accelerating the universe's expansion, possibly stretching this region thin long before galaxies could form. Some even speculate, though it's a long shot, that the void could be evidence of an unfathomably advanced civilization that somehow harvested the matter there, leaving behind a sterile bubble. But perhaps the most unsettling possibility is that the Boötes Void isn't alone. Astronomers have found other, smaller voids scattered throughout the universe, hinting that these cosmic deserts might be more common than we thought. They challenge our understanding of how matter distributes itself, forcing us to reconsider whether the universe's structure is as predictable as we once believed. And that's what makes the Boötes Void so captivating. It's not just an absence, it's a cosmic riddle written in negative space, daring us to question what we think we know about the fabric of reality itself. While the Boötes Void captivates with its staggering emptiness, there's another cosmic desert much closer to home, one we're actually drifting through right now. Meet the KBC Void, an immense bubble of space named after astronomers Keenan, Barger, and Cowie, who identified it in 2013. Unlike its distant cousin, this void isn't just a curiosity. It's our galactic neighborhood's backyard, stretching roughly 2 billion light-years across, with the Milky Way sitting near its center. Imagine floating in the middle of a hollow sphere so vast that entire galaxy clusters dot its edges like distant campfires, while you're left in near total darkness. That's the KBC Void. At first glance, it might seem less extreme than the Boötes Void, but its implications are far more personal. For one, it challenges the cosmological principle, the long-held assumption that, on large enough scales, the universe looks roughly the same in every direction. If matter were evenly distributed, we wouldn't find ourselves in such a conspicuously empty pocket. Instead, the KBC Void suggests a lumpy, uneven cosmos where some regions are densely packed with galaxies, while others, like ours, are startlingly sparse. It's as if we've won a cosmic lottery no one knew existed, the prize being isolation on a scale that defies probability. What makes this void especially puzzling is how it reshapes our understanding of cosmic expansion. Measurements of the Hubble constant the rate at which the universe is stretching vary depending on where and how we observe it. Some scientists argue our location in this void might be skewing those measurements, like trying to gauge the speed of a river while drifting in a slow-moving eddy. If true, it could help explain one of astronomy's biggest headaches, the Hubble tension, where different methods yield conflicting results about how fast the universe is growing. Then there's the eerie symmetry. The KBC Void isn't just empty, it's nested within a series of larger structures like a Russian doll of cosmic voids. Some researchers propose this hierarchy hints at deeper patterns in the universe's architecture, possibly even relics of quantum fluctuations from the Big Bang itself. Others wonder if dark energy, the mysterious force accelerating cosmic expansion, behaves differently in these underpopulated regions, stretching them even faster into oblivion. So why haven't we heard more about this void? Unlike the Boötes void, which announces itself with dramatic emptiness, the KBC void is subtler, its edges blending into the cosmic web. Mapping it required painstaking surveys of galaxy distributions, revealing our place in this quiet corner almost by accident. Yet its existence forces us to confront an unsettling idea. We might not be in a typical part of the universe at all. Instead, we're outliers in a grand celestial tapestry, living in a bubble so odd it makes us question whether we've misunderstood the cosmos all along. And if that's true, what other surprises are hiding in the voids we've yet to discover? Hidden behind a swirling veil of stars and cosmic dust lies one of astronomy's most frustrating blind spots, the Zone of Avoidance. Stretching along the dense plane of our Milky Way, this region blocks our view of the universe beyond like a celestial curtain, obscuring nearly 20% of the night sky. Imagine trying to study a distant city through a snowstorm. That's the challenge astronomers face when peering into this zone. The sheer concentration of gas, dust, and stars in our galaxy's disk absorbs and scatters visible light, rendering entire swaths of the cosmos invisible to traditional telescopes. For centuries, this area remained a literal dead end for exploration, a blank spot on the map where conventional observation simply couldn't penetrate. But where visible light fails, ingenuity steps in. Modern astronomers have turned to infrared and radio telescopes, tools that can cut through the cosmic fog like headlights piercing a misty night. Infrared light, with its longer wavelengths, slips past dust particles that would block ordinary light, revealing galaxies previously lost in the glare. Radio waves go even further, exposing the hidden structures lying in wait behind the Milky Way's glare. And what they've found is astonishing. Entire galaxies, some massive, some peculiar, have been lurking just out of sight, their presence betrayed only by subtle distortions in the radio waves they emit. One of the most dramatic discoveries came in the 1980s when researchers detected the Dwinjaloo 1 and 2 galaxies, two spiral systems eerily similar to our own, hiding just beyond the zone's dust. What makes these findings so thrilling is what they imply about the universe's structure. The Zone of Avoidance isn't just an empty gap, it's a treasure trove of unseen cosmic architecture. Some theories suggest it might conceal part of the Great Attractor's hidden mass, or even undiscovered filaments of the cosmic web that binds galaxies together. Every new observation peels back another layer of mystery, hinting that the universe beyond our galactic fog could be far richer and more complex than we ever imagined. Yet the challenge remains immense. Even with advanced technology, mapping this zone is painstaking work, requiring telescopes to stitch together fragmentary glimpses into a coherent picture. It's a reminder that sometimes the universe's greatest secrets aren't just at the edge of the observable cosmos, they're right in front of us, cloaked in the very fabric of our own celestial home. And with each breakthrough, we're not just filling in blank spaces on a map, we're rewriting the story of the cosmos itself. The universe is supposed to expand evenly in all directions, a fundamental rule written into the fabric of space itself. But something out there is breaking that rule. Meet the dark flow, a phenomenon so strange it feels ripped from science fiction. Hundreds of galaxy clusters, each containing thousands of galaxies, are drifting in the same direction at staggering speeds, like leaves caught in a cosmic river no one can see. This isn't just random motion, it's a coordinated march towards something beyond the edge of the observable universe, something so massive its gravitational pull defies everything we know about the cosmos. The dark flow was discovered in 2008 when astronomers noticed something odd in the afterglow of the Big Bang. By studying the cosmic microwave background, the faint echo of the universe's birth, they spotted subtle distortions in the motion of galaxy clusters. These distortions pointed unmistakably toward a single patch of sky near the constellations Centaurus and Vela. The clusters weren't just moving, they were being pulled as if by an invisible hand. The kicker, there's nothing there, at least nothing we can detect. No supercluster, no concentration of dark matter, nothing that could explain the force required to tug entire clusters millions of light years off course. One explanation pushes the boundaries of physics itself. The dark flow might be evidence of a structure so colossal it lies beyond our cosmic horizon. Picture a mountain so vast you can only see its shadow. That's what some theorists suggest. This unseen behemoth could be a megacluster of galaxies or a knot of dark matter trillions of times more massive than anything we've encountered, lurking just outside the observable universe. Its gravity would ripple across the void, nudging galaxy clusters like a magnet tugging at iron filings. But there's a wilder possibility. Some scientists speculate the dark flow could be the gravitational imprint of another universe, a neighboring bubble in the multiverse brushing against our own. If true, it would mean we're not just mapping the unknown, we're glimpsing the edges of reality itself. Critics argue the data might be a statistical fluke, an illusion created by incomplete observations. Yet the more we study it, the harder it becomes to dismiss. The dark flow persists in newer surveys, its signals stubbornly real. What makes this mystery so electrifying is what it implies about our place in the cosmos. We're used to thinking of the universe as a self-contained arena, everything we'll ever know contained within its expanding walls. But the dark flow hints at something grander, a cosmic tapestry woven with threads we can't yet see. Whether it's an unseen structure or a door to another universe, one thing is clear. The universe still has secrets we've only begun to uncover. And if we ever solve this puzzle, the answer might rewrite not just astronomy, but our very understanding of existence. Rising from the heart of the Milky Way like twin titans, the Fermi bubbles stretch 50,000 light-years into space, one erupting above the galactic plane, the other below. These colossal structures, invisible to the naked eye, glow fiercely in gamma rays, the highest energy light the universe produces. Picture two cosmic hourglasses pressed back to back, their searing edges tracing a faint but defiant outline against the darkness. Discovered in 2010 by NASA, a Fermi Gamma-Ray Space Telescope, these bubbles have puzzled astronomers ever since. How could something so massive, so energetic, exist right in our celestial backyard without us noticing for so long? Their origin story reads like a cosmic detective novel with two leading suspects. The first, our galaxy's supermassive black hole, Sagittarius, a star. Though quiet today, it might have erupted in a cataclysmic feeding frenzy millions of years ago, belching out jets of ultra-fast particles that inflated these bubbles like cosmic balloons. Evidence for this lies in the bubble's symmetrical structure and their intense gamma-ray emissions, hallmarks of particles accelerated to nearly the speed of light. Some simulations even suggest the black hole's last major outburst could have been as recent as 2 million years ago, a blink in cosmic time. But there's another possibility. These bubbles could be fossils of a golden age of star formation. When massive stars are born in droves, they live fast, die young, and explode as supernova, flooding their surroundings with shockwaves and radiation. Over eons, these collective outbursts might have sculpted the bubbles, like a galactic wind carving cavities into the surrounding gas. Supporting this idea are observations of similar, smaller structures in other galaxies, where frenzied star birth seems to have blown cosmic bubbles of its own. The debate gets even more intriguing when you consider what the bubbles contain, or rather, what they don't. Their interiors are strangely empty, devoid of the usual interstellar gas that fills the rest of the galaxy. Instead, they're lined with a thin shell of high-energy particles, like the shimmering surface of a soap bubble. And then there's the mystery of their edges, razor sharp in some regions, frayed in others, as if whatever created them didn't act uniformly. It's a clue that the truth might lie somewhere between the two theories, perhaps a black hole eruption interacting with pre-existing stellar winds, creating a hybrid structure no one predicted. What makes the Fermi bubbles so compelling isn't just their scale or their energy, it's what they reveal about our galaxy's volatile past. We tend to think of the Milky Way as a stable, almost serene place, but these bubbles are a reminder that it's a dynamic, even violent ecosystem. They're a snapshot of a time when forces beyond our comprehension reshaped the galaxy, leaving behind echoes we're only now learning to read. And as astronomers peer deeper into their gamma-ray glow, they're not just studying ancient history, they're uncovering the invisible forces that still shape the cosmos around us. At the very heart of our galaxy, hidden behind thick curtains of dust and scorching radiation, lurks a monster Sagittarius, a star. This supermassive black hole, weighing in at 4 million times the mass of our Sun, anchors the Milky Way in an invisible grip of gravity so intense it bends light itself. Yet for all its power, Sagittarius, a star, is strangely quiet, like a sleeping giant. Most of the time, it emits barely a whisper of energy, a faint glow against the riot of stars crowding the galactic center. But don't let its calm demeanor fool you. This black hole has a violent past, and its surroundings are a cosmic war zone where the laws of physics unravel. What makes Sagittarius, a star, so enigmatic isn't just its size, but its contradictions. Supermassive black holes in other galaxies often blaze with energy, devouring matter in spectacular outbursts that outshine entire constellations. Yet ours lingers in a peculiar state of hibernation, only occasionally snacking on stray gas clouds or stars that wander too close. When it does feed, the results are dramatic. In 2019, astronomers witnessed a mysterious flare, a sudden burst of infrared light so bright it doubled the black hole's normal glow in just 2 hours. The cause, possibly a shredded star or a clump of gas spiraling into oblivion, torn apart by tidal forces strong enough to stretch atoms like taffy. Exploring this region is like trying to study the eye of a hurricane. The galactic center is bathed in lethal radiation, X-rays, gamma rays, and cosmic particles accelerated to near light speed. Even our most hardened spacecraft wouldn't last long in this environment. Then there's the gravitational chaos. Stars orbiting Sagittarius, a star, whip around at thousands of kilometers per second, their paths twisted into bizarre loops by the black hole's pull. One star, known as S2, completes its breakneck orbit in just 16 years, a cosmic sprint that defies intuition. Yet the greatest mystery lies in the silence. Why isn't Sagittarius, a star, more active? Some theories suggest it starved. Most of the gas in the galactic center has been blown away by stellar winds or locked up in stars. Others propose its magnetic field acts like a cosmic dam, preventing matter from falling inefficiently. Then there's the chilling possibility that we're simply witnessing a lull between eruptions, and the black hole could wake with a vengeance at any moment. Peering into this maelstrom requires more than just telescopes. It demands ingenuity. Infrared instruments like the Event Horizon Telescope have pierced the dust to capture the black hole's shadow, a dark silhouette ringed by glowing gas. Radio telescopes map the twisted magnetic fields that channel matter into the abyss. Each observation reveals another piece of the puzzle, but Sagittarius, a star, guards its secrets fiercely. It's a reminder that even in our own galactic backyard, there are frontiers so extreme, so hostile, they might remain unexplored for centuries. And yet, hidden in its depths could be answers to the universe's biggest questions: how galaxies form, how black holes shape their surroundings, and what happens when matter crosses the point of no return. The far side of the moon has always been a cosmic enigma, a face forever turned away from Earth, shrouded in mystery. Unlike the familiar craters and seas of the near side, this hidden hemisphere remained completely unexplored until the dawn of the space age, locked in place by a phenomenon called tidal locking. The Moon's rotation matches its orbit around our planet so precisely that we only ever see one side, like a dancer spinning perfectly in sync with their partner, always presenting the same view. But this celestial ballet isn't just a quirk of gravity. It's a barrier that kept half of our closest cosmic neighbor invisible to humanity for millennia. Breaking through that barrier requires overcoming immense challenges. Communication with the far side is impossible without relay satellites, since direct radio signals from Earth can't pierce the Moon's bulk. China's Chang'e 4 mission, the first to land softly on this uncharted terrain in 2019, had to deploy a dedicated satellite named Queqiao to bounce signals back to Earth, a celestial intermediary bridging the gap. The lander's discoveries were groundbreaking, unveiling a landscape utterly different from the near side, with a thicker, more rugged crust and fewer of the dark volcanic plains that define the face we know. But why is the far side so distinct? One theory points to Earth's gravitational influence during the Moon's infancy, when its molten surface was still cooling. The near side, tugged by our planet's gravity, may have thinned and cracked, allowing lava to well up and form the smooth basins we see today. The far side, shielded from this pull, remained intact, preserving its ancient, battered surface like a time capsule from the solar system's violent early days. Recent missions have only deepened the intrigue. Chang'e 4's rover U-22 stumbled upon a strange gel-like substance in a small crater, later identified as impact melt glass, a remnant of a long-ago collision. Then there's the South Pole Aitken Basin, one of the largest impact craters in the solar system, spanning nearly a quarter of the Moon's surface. This colossal scar, buried on the far side, exposes layers of the lunar mantle usually hidden deep below, offering scientists a rare window into the Moon's inner composition. Yet for all we've learned, the far side remains a frontier. Its radio-quiet environment, shielded from Earth's incessant transmissions, makes it an ideal spot for telescopes that could peer into the universe's darkest corners. Future missions might uncover more secrets, from water ice hidden in permanently shadowed craters to clues about how tidal locking shaped not just the Moon, but countless other worlds across the cosmos. It's a reminder that sometimes the greatest mysteries aren't found in the depths of space, but right next door, lurking just out of view. Beyond the familiar orbits of planets and asteroids, far past even the icy realm of Pluto, lies a place so distant it exists more in theory than observation: the Oort Cloud. This vast spherical shell of frozen debris is thought to encircle our solar system like a cosmic moat, stretching nearly halfway to the nearest star. Named after Dutch astronomer Jan Oort, who proposed its existence in the 1950s, this region remains one of the last uncharted frontiers of our own cosmic neighborhood. No spacecraft has ever reached it, no telescope has ever glimpsed it directly. Yet its influence is everywhere. Swarms of long-period comets, those ghostly visitors that streak through our skies once every few centuries, are believed to originate from this frozen reservoir at the edge of the Sun's grasp. The Oort Cloud's elusiveness comes down to sheer distance and darkness. Imagine trying to spot a snowflake in a blizzard from thousands of miles away. That's the challenge astronomers face. The cloud's innermost edge might begin around 2,000 astronomical units from the Sun, 1,0 being the distance from Earth to the Sun, but its outer reaches could extend 100 times farther. At those distances, even the largest icy objects would reflect almost no sunlight, rendering them invisible to current technology. The few traces we have come from indirect clues, the peculiar orbits of comets like Hale-Bopp, which loop in from deep space on paths suggesting a distant spherical source rather than the flatter Kuiper belt. What's truly staggering is the scale of this hypothesized structure. If the Oort Cloud exists as theorized, it could contain trillions of icy bodies, remnants from the solar system's violent birth 4.5 billion years ago. These aren't just frozen leftovers, they're time capsules, preserving the pristine chemistry of the early solar system. When a passing star's gravity nudges one inward, it becomes a long-period comet, thawing as it approaches the Sun and revealing gases and dust unchanged since the planet's formed. That's why missions like Europe's Rosetta, which studied comet 67P, are so vital. They're sampling pieces of the Oort Cloud without needing to travel there. Yet mysteries abound. Why haven't we detected even the largest Oort Cloud objects? Some models suggest they might be darker than expected, coated in organic compounds that absorb light. Others propose the cloud isn't uniformly distributed but clumped, shaped by galactic tides or ancient encounters with passing stars. There's even a fringe theory that a hidden planet, a true Planet 9, could be shepherding these icy bodies into odd orbits from the shadows. The Oort Cloud's most tantalizing role might be as a celestial conveyor belt. Occasionally, a star drifting nearby could perturb the cloud, sending a hail of comets inward, some to dazzle us with their brilliance, others potentially threatening Earth. It's a reminder that even in our quiet corner of the galaxy, we're not isolated. The Oort Cloud binds us to the wider cosmos, a fragile bridge between the Sun's warm embrace and the interstellar unknown. Until we develop telescopes powerful enough to pierce that darkness, or spacecraft hardy enough to endure the journey, it remains a hypothesis wrapped in ice and mystery, a frontier at our doorstep, yet still just out of reach. The Pioneer Anomaly is one of those cosmic puzzles that refuses to fade into obscurity, a tiny deviation in the paths of two spacecraft that sent shockwaves through the world of physics. Launched in the 1970s, Pioneer 10 and 11 were humanity's first emissaries to the outer solar system, tasked with studying Jupiter, Saturn, and the space beyond. But as they ventured farther from Earth, something unexpected happened. Both probes began slowing down slightly more than predicted, as if an invisible hand were tugging them backward. The discrepancy was minuscule, about 300,000 times weaker than Earth's gravity, but it was consistent, unexplained, and utterly perplexing. For decades, scientists scrutinized every possible cause. Could it be fuel leaks, electrical glitches? Even the gentle push of sunlight bouncing off the probe's surfaces was considered. But none of these accounted for the anomaly. The real breakthrough came when researchers realized the deceleration wasn't just random noise, it was a constant sunward tug, as if the probes were caught in some unseen gravitational current. That's when the theories took a wild turn. Some suggested thermal radiation, heat radiating unevenly from the spacecraft's power systems, might be generating enough recoil to explain the drift. Others wondered if dark matter, that elusive cosmic ghost, might be clustering around our solar system, dragging on the pioneers as they passed through it. The most tantalizing possibility, though, was that the anomaly hinted at a flaw in our understanding of gravity itself. Could Einstein's theory of general relativity, the bedrock of modern physics, need tweaking at the scale of the solar system? Modified Newtonian dynamics, or MUND, a controversial framework proposing adjustments to gravity's behavior in weak fields, gained traction as a potential explanation. For a brief moment, it seemed like the Pioneer Anomaly might be the thread that unraveled our cosmic rulebook. Then, in 2012, a painstaking analysis pointed to a far more mundane culprit: heat. By reconstructing the probe's thermal emissions in unprecedented detail, a team showed that radiation from their plutonium power sources could, in fact, produce just enough recoil to match the observed deceleration. Case closed, not quite. Skeptics noted that the thermal explanation didn't perfectly align with all the data, leaving lingering doubts. And even if heat was the primary cause, the anomaly's precise magnitude still didn't add up neatly. What makes the Pioneer Anomaly so enduring isn't just the mystery itself. It's the reminder that even in an age of precision engineering and hyper-accurate simulations, the universe can still surprise us. Those two aging probes, now drifting silently in the interstellar dark, may have inadvertently exposed a crack in our cosmic knowledge, however small. Whether the final answer lies in thermal physics, unseen matter, or something far stranger, their legacy endures, a testament to the fact that sometimes the biggest revelations come from the tiniest deviations. On the evening of August 15, 1977, a radio telescope in Delaware, Ohio, picked up something extraordinary, a signal so powerful, so unusual, that the astronomer who discovered it circled the printout in red pen and wrote a single word beside it: "Wow." This wasn't just another blip in the cosmic static. It was a narrowband radio burst at exactly the frequency hydrogen emits naturally, a frequency scientists had long theorized might be used by extraterrestrial civilizations trying to broadcast their presence. For 72 unforgettable seconds, the signal blazed brighter than anything in the sky around it, then vanished as suddenly as it appeared. Decades later, the WOW signal remains astronomy's most tantalizing ghost, a whisper from the void that refuses to be explained. What made this signal so special wasn't just its intensity, but its precision. It appeared at 1,420 MHz, a quiet spot in the radio spectrum where natural cosmic noise is minimal, making it an ideal cosmic hailing frequency. The signal's bandwidth was narrower than any known natural phenomenon, almost exactly what you'd expect from an engineered transmission. Even stranger, it followed the motion of the sky, rising and falling in strength as the telescope scanned, a telltale sign it originated in deep space rather than from Earth's surface or nearby satellites. For those 72 seconds, it seemed like we might have finally caught the universe's attention. Yet every attempt to find it again has failed. Astronomers have pointed telescopes at the same patch of sky, a region near the constellation Sagittarius, hundreds of times, listening for a repeat that never comes. Some have suggested the signal could have been a reflected Earth-bound transmission, bouncing off space debris, but the frequency used was protected by international agreement, reserved exclusively for astronomy. Others propose a comet might have been the culprit, but none were known to be in that area of the sky at the time. The leading natural explanation points to a rogue hydrogen cloud heated by a passing star, briefly glowing at that specific frequency. But such an event would be incredibly rare, and no one's ever observed anything like it since. Then there's the unnerving possibility the signal was exactly what it seemed, a deliberate broadcast. If so, why hasn't it repeated? One theory suggests it could have been a one-time beacon, sweeping across the galaxy like a lighthouse beam, briefly illuminating Earth before moving on. Another imagines a civilization that briefly powered up a transmitter, perhaps for their own purposes, unaware they'd caught our attention. The most haunting idea is that the signal was meant for someone else entirely, and we simply overheard a cosmic conversation not meant for our ears. The WOW signal's legacy isn't just about what we heard, it's about what we didn't. Its silence since then is a reminder of how vast and quiet the universe truly is, and how fragile our attempts to find company in the darkness might be. But it's also a beacon of hope, proof that sometimes the cosmos sends us puzzles that defy easy answers, keeping the wonder alive, until another signal breaks the silence, that lone red wow. On a decades-old printout remains our best clue that we might not be alone, and that the universe still has stories left to tell. Stretching across 10 billion light-years of cosmic real estate, the Hercules Corona Borealis Great Wall isn't just large, it defies our very understanding of what large should mean. Discovered in 2013 by mapping gamma-ray bursts, this galactic megastructure is a filament of galaxies so vast it would take light, the fastest thing in the universe, nearly 3/4 of cosmic history just to traverse it from end to end. To put that in perspective, if our Milky Way were the size of a grape, this wall would span the width of the entire United States. It's a staggering reminder that the universe's grandeur operates on scales our minds can barely grasp. But here's the problem: structures this enormous shouldn't exist. at least not according to the cosmological principle, one of astronomy's foundational ideas. This principle states that on sufficiently large scales, the universe should appear roughly uniform. No dramatic clumps, no gaping voids, just an even distribution of matter. Yet the Hercules Corona Borealis Great Wall flouts this rule spectacularly, standing as a glaring exception to cosmic uniformity. It's like stirring a cup of coffee only to find all the sugar clumped into a single, unmoving mass at the bottom. How could something so colossal form? One theory suggests it's a fossil of the universe's infancy, a relic from when quantum fluctuations in the primordial soup of the Big Bang planted the seeds for later structure. Over billions of years, gravity amplified these tiny ripples into the vast web of galaxy filaments we see today, with the Hercules Corona Borealis Wall as its most extreme example. Others argue it might not be a single structure at all, but a chance alignment of smaller filaments viewed from our vantage point, like mistaking a series of mountain ranges for one unbroken chain. Then there's the unsettling possibility that our models are incomplete. Could dark energy, the mysterious force accelerating the universe's expansion, play a role in sculpting such giants? Or might there be unknown forces at work in the early universe that left behind these cosmic anomalies? The debate rages because the implications are profound. If the cosmological principle doesn't hold, our entire framework for understanding the universe's evolution might need rethinking. What makes this wall so mesmerizing isn't just its scale, it's the questions it forces us to confront. Are we seeing the universe as it truly is, or are we limited by the tools and theories we've built to comprehend it? Every new observation peels back another layer, revealing a cosmos far stranger, far more intricate than we ever imagined. And somewhere in that complexity, hidden among the galaxies of this unimaginable wall, might lie clues to the universe's deepest secrets, if only we can decipher them. Deep in the cosmic microwave background, the faint afterglow of the Big Bang itself, there's a mysterious cold spot that refuses to fit neatly into our understanding of the universe. Stretching nearly 1.8 billion light-years across, this anomaly, aptly named the cold spot, isn't just a minor temperature fluctuation. It's a blistering headache for cosmologists. While the rest of the microwave sky shows tiny variations, this region is colder than it has any right to be, as if someone left a cosmic refrigerator door ajar in an otherwise uniform cosmic oven. One leading theory suggests the cold spot might be the shadow of a supervoid, an enormous, near-empty region of space where galaxies are few and far between. In such a void, light traveling through it would lose energy as the universe expands, a phenomenon known as the integrated Sachs-Wolf effect. Think of it like climbing a hill only to find the other side has eroded away. The light arrives weaker, cooler than it should. But here's the catch. The largest known voids are still too small to explain the cold spot's staggering size and temperature drop. If a supervoid is responsible, it would have to be so vast and empty it challenges our models of how structure forms in the universe. That's where things get wild. Some physicists propose an even more radical explanation. The cold spot could be a bruise from a collision with another universe. In the multiverse theory, our cosmos might be one bubble among countless others in an infinite froth of realities. If another bubble universe grazed ours in the distant past, the energy of that impact could have left behind a temperature anomaly, like a fingerprint on glass. It's a speculative idea, but not impossible. The cold spot's unusual polarization patterns detected by Planck satellite data don't match typical voids, giving this theory just enough credibility to keep scientists debating. Yet skeptics point out simpler possibilities. Could it be an artifact of how we're interpreting the data, or an unlikely statistical fluke in an otherwise uniform cosmos? After all, when you're mapping the entire observable universe, there's bound to be at least one outlier, but the cold spot refuses to be dismissed so easily. Its sheer size and the precision of its temperature dip make it a persistent thorn in the side of standard cosmology. What makes this cosmic oddity so compelling isn't just the mystery, it's the stakes. If the supervoid explanation holds, we might need to rethink how large-scale structures evolve. If it's evidence of a multiverse, it would be our first glimpse beyond the borders of reality as we know it. For now, the cold spot remains an open question, a patch of sky that's too cold, too strange, and too defiant to ignore. And in that defiance, it reminds us that the universe still has the power to surprise. The universe keeps meticulous balance sheets, every proton, every neutron, every particle of ordinary matter accounted for in the grand cosmic ledger, or so we thought. When astronomers tallied up all the visible stars, gas, and dust in the universe, they stumbled upon an unsettling discrepancy: about 30 to 40% of the ordinary matter. The baryons that make up everything from planets to people was simply missing. No glow, no shadow, no trace in any telescope's gaze. This is the missing baryon problem, a cosmic accounting error that's had scientists scratching their heads for decades. So where did all that matter go? One leading suspect is the warm-hot intergalactic medium, or WIM, a faint, diffuse web of superheated gas stretching between galaxies. Picture steam rising from a cup of tea, but on a scale so vast it fills the voids between galaxy clusters. This gas isn't cold enough to form stars, nor dense enough to glow brightly, but it's everywhere, threaded through the cosmos like an invisible scaffolding. The catch: detecting it is like trying to spot fog in the dark. The WIM temperature between 100,000 and 10 million degrees means it emits mostly X-rays, a wavelength range that's notoriously difficult to observe from Earth's surface due to atmospheric absorption. Recent breakthroughs, however, are turning the tide. By studying the distorted light of distant quasars as it passes through these filaments, astronomers have spotted subtle absorption lines, telltale fingerprints of ionized oxygen and other elements in the WIM. It's like finding wet footprints leading through a desert. The gas itself remains invisible, but its effects betray its presence. Even more compelling are observations from X-ray telescopes like Chandra and XMM Newton, which have caught faint glimmers of the WIM emissions in the spaces between galaxy clusters. These findings suggest the missing baryons might not be missing at all, just hiding in plain sight, woven into the fabric of intergalactic space, but the plot thickens. Some simulations suggest the WIM might not account for all the missing matter. Alternative hideouts include the outskirts of galaxies, where vast halos of hot gas could lurk undetected, or even within dwarf galaxies too dim for current telescopes to spot. There's also the unsettling possibility that some baryons have been pushed out of the observable universe entirely, carried beyond our cosmic horizon by the accelerating expansion of space. What makes this mystery so gripping isn't just the hunt for hidden matter, it's the implications. If the WIM holds most of these missing baryons, it means the universe's large-scale structure is far more dynamic than we imagined, with gas constantly cycling between galaxies and intergalactic space. It also forces us to confront the limits of our tools. The same telescopes that can pinpoint galaxies billions of light years away struggle to see the hot gas in our cosmic backyard. The search for these lost baryons is more than a cosmic scavenger hunt. It's a test of our understanding of how the universe organizes itself. And with every new observation, we're peeling back another layer of the invisible framework that binds the cosmos together. Whether the final answer lies in the WIM or somewhere even more elusive, one thing is certain: the universe still has a few tricks up its sleeve. We live nestled inside a cosmic giant, the Laniakea supercluster, a sprawling archipelago of galaxies spanning 500 million light-years. Its name, derived from Hawaiian, means immeasurable heaven, a fitting title for a structure so vast it contains roughly 100,000 galaxies, including our own Milky Way. But here's the twist: defining the edges of this celestial metropolis isn't as simple as drawing lines on a map. Unlike the crisp borders of countries or continents, superclusters blend into one another like watercolors on a cosmic canvas, their boundaries determined not by sight but by the invisible tug of gravity. Imagine the universe as a rushing river with galaxies floating like leaves caught in its current. Laniakia's boundaries are traced by the subtle flow of these galactic streams, all moving together toward a common center of gravity. In the 1980s, astronomers noticed something peculiar. Galaxies across our local universe weren't just drifting randomly, they were converging as if pulled by an unseen force. This revelation reshaped our cosmic address, placing us not just in the Milky Way or the Virgo cluster, but within a supercluster of staggering scale. At the heart of Laniakia's motion lies the Great Attractor, that enigmatic gravitational anomaly we explored earlier. Like a cosmic siren, it pulls Laniakia's galaxies toward it at over 600 kilometers per second, a silent current shaping the paths of everything from the smallest dwarf galaxies to the largest clusters. But the Great Attractor isn't acting alone. Recent studies suggest an even more distant and massive structure, the Shapley supercluster, may be amplifying this pull, a reminder that gravity's reach extends far beyond what we can see. What makes Laniakia so fascinating isn't just its size but its dynamism. Superclusters aren't static kingdoms, they're evolving tapestries woven together by the ebb and flow of dark matter and dark energy. Some regions collapse inward, forming dense knots like the Virgo cluster, while others stretch into filaments, thin threads of galaxies connecting one node to another. We're riding this cosmic web, hurtling through space not as isolated wanderers but as part of a grand gravitational dance. Yet for all its grandeur, Laniakia is just one thread in an even larger tapestry. Beyond it lie other superclusters, Perseus Pisces, Coma, Hercules, each with its own gravitational signature. One day, as the universe expands, these titanic structures may grow isolated, islands adrift in an ever-darkening sea. But for now, they remind us that the cosmos is alive with motion, a reminder that even the stars above us are part of something far greater, a story written in gravity and time, unfolding on scales the human mind can scarcely comprehend. Every galaxy, including our Milky Way, is cocooned inside an invisible shroud, a vast, diffuse sphere of dark matter stretching far beyond the visible stars. This mysterious halo doesn't emit light, absorb it, or reflect it. It doesn't even collide with ordinary matter in any meaningful way. Yet its gravitational grip is so powerful it dictates the very shape and motion of galaxies, bending the fabric of space itself to keep stars from flying apart. Without these halos, galaxies as we know them wouldn't exist. They're the hidden architects of the cosmos, the unseen scaffolding holding everything together. Detecting something that refuses to interact with light is no small feat. Astronomers first stumbled upon dark matter's existence in the 1930s, when Fritz Zwicky noticed galaxies in the Coma cluster were moving far too quickly to be held together by the gravity of visible matter alone. Decades later, Vera Rubin's observations of spinning galaxies confirmed its stars at the edges were orbiting just as fast as those near the center, defying Newton's laws unless some invisible mass was propping up the system. Today, we map these halos using tricks of gravity's handiwork. When light from distant galaxies passes near a dark matter halo, it bends like a straw in a glass, a phenomenon called gravitational lensing. By measuring these distortions, we can trace the halo's mass like a sculptor feeling the contours of clay. The real wonder lies in how these halos shape the universe's grand design. Dark matter doesn't just cling to galaxies, it forms an intricate cosmic web, a sprawling network of filaments connecting clusters and superclusters across billions of light years. In the early universe, dark matter's gravity acted as a cosmic glue, pulling ordinary gas into its embrace, where it cooled and collapsed into the first stars and galaxies. Simulations show this process vividly. Dark matter's tendrils knot together, creating dense nodes where galaxies bloom like dew on a spiderweb, but the halos themselves are full of puzzles. Why do they have such smooth cores when simulations predict sharp density spikes? Some theories suggest dark matter particles might interact weakly with each other, scattering like billiard balls and smoothing out the center. Others posit that feedback from supernova or black holes churns up the inner regions, redistributing the invisible mass. Then there's the haunting possibility that we've misunderstood dark matter entirely, that it's not a single particle but a mix of different, even stranger components. What's clear is that these halos are more than passive backdrops. They're dynamic, evolving entities growing through collisions and mergers. When two galaxies meet, their dark matter halos intertwine like mist, sometimes stripping stars from one another in dazzling tidal streams. Our own Milky Way's halo is likely studded with the remnants of smaller galaxies it's consumed over billions of years, a fossil record written in gravity's ink. The search for dark matter's true nature continues, from detectors buried deep underground to telescopes scanning the skies. With every new observation, we're not just hunting for invisible particles, we're piecing together the hidden framework that built the universe. And somewhere in that vast, uncharted halo surrounding us, the answers may be waiting, silently shaping the stars above. At the heart of every black hole, buried beneath the event horizon where gravity's grip becomes inescapable, lies a mystery that could rewrite physics itself, the Planck star. This hypothetical object isn't some exotic cosmic gem, but the last gasp of a collapsing black hole, a relic so dense and strange it defies everything we know about space and time. Picture a dying star's core, crushed beyond recognition by its own gravity, but instead of vanishing into a singularity, a point of infinite density, it rebounds at the smallest possible scale the universe allows. That rebound is the Planck star, a fleeting moment where quantum gravity takes over, resisting collapse with a force even gravity can't overcome. The idea stems from loop quantum gravity, a theory that reimagines space itself as a fabric woven from microscopic, indivisible threads. Unlike classical physics, where matter crushed in a black hole spirals endlessly toward a singularity, this framework suggests space has a built-in springiness. When compression reaches the Planck scale, a distance so small it's a trillion times tinier than an atom, the fabric of spacetime pushes back, halting the collapse like a trampoline catching a falling weight. For an instant, the dying star becomes a Planck star, burning with temperatures hotter than the Big Bang before bouncing outward in a cosmic reversal. What makes this concept so tantalizing isn't just its defiance of singularities, it's the echoes it might leave behind. Some theorists propose that these rebounds could explain fast radio bursts, those enigmatic blips of energy from deep space, or even serve as the seeds for new universes. Imagine a black hole's death not as an end but as a cosmic reset button, its Planck star birthing a new spacetime bubble in an unfathomable multiverse. Yet for all its elegance, the Planck star remains a ghost in the equations. No telescope can peer inside a black hole to confirm it, and no experiment on Earth can recreate the conditions needed to test loop quantum gravity's predictions. Even Hawking radiation, the faint glow emitted by black holes as they evaporate, offers no direct clues. The only hints lie in the subtle signatures in gravitational waves or the afterglow of black hole mergers that future observatories might one day detect. But the implications are staggering. If Planck stars exist, they'd bridge the chasm between quantum mechanics and general relativity, two theories that have resisted unification for a century. They'd prove that spacetime isn't infinitely divisible but granular, a pixelated reality where gravity and quantum forces finally shake hands, and they'd transform black holes from bottomless pits into cosmic phoenixes, collapsing and reborn in a cycle as old as the universe itself. Until then, the Planck star lingers at the edge of imagination, a reminder that some of the universe's deepest truths might be hiding not in the distant cosmos, but in the heart of darkness we've yet to fully explore. Beyond the known planets, far past Neptune's icy realm, something massive might be lurking in the darkness, an unseen world with 10 times the mass of Earth, silently sculpting the orbits of distant objects. This is Planet 9, a hypothetical giant that astronomers have hunted for nearly a decade, not with telescopes but through the subtle disturbances it leaves in its wake. The evidence lies in the strange behavior of icy bodies in the Kuiper belt, a ring of frozen debris at the solar system's edge. Several of these objects, like the dwarf planet Sedna, follow elongated orbits that cluster in a way that defies random chance, as if an invisible hand were herding them. The math behind Planet 9's proposed orbit is just as fascinating as the hunt itself. Simulations suggest it could orbit the Sun at an average distance 20 times farther than Neptune, completing a single lap around the Sun every 10 to 20,000 years. Its path would be highly elliptical, swinging far out into the void before diving back toward the inner solar system. But here's the catch: because of its extreme distance, sunlight reaching Planet 9 would be so faint that spotting it would be like trying to find a single dim light bulb lost in the glare of a city skyline. Even our most powerful observatories, like the Subaru telescope in Hawaii, have only managed to rule out small patches of sky where it isn't hiding. What makes this search so maddening is the sheer scale of the haystack. Planet 9's orbit could take it anywhere along a vast celestial highway, and with each passing year, its position changes, meaning astronomers are chasing a moving target in near total darkness. Some researchers have turned to alternative methods, like searching for heat signatures in infrared, but even those efforts have come up empty so far. Skeptics argue the clustering of Kuiper belt objects could be a statistical fluke, or perhaps the gravitational influence of many smaller bodies combined. Yet the patterns persist, and with every new oddball object discovered, like the highly tilted orbit of 2015 BP 519, the case for Planet 9 grows stronger. If it exists, this world wouldn't just be a curiosity, it would rewrite the story of our solar system's formation. A planet of that size, that far out, likely didn't form in place. Instead, it might have been flung outward by Jupiter or Saturn's gravity in the solar system's chaotic youth, a cosmic outcast finding refuge in the frozen dark. Or perhaps it's a rogue planet captured from another star long ago. Whatever its origin, its discovery would offer a missing piece in the puzzle of how planetary systems evolve, and remind us that even in our own celestial neighborhood, the final chapter of exploration is far from written. Until then, Planet 9 remains a ghost in the equations, a whisper of gravity in the outer dark, daring us to look deeper. The cosmic microwave background, the oldest light in the universe, should be a chaotic fingerprint of the Big Bang's aftermath, a random splatter of hot and cold spots left over from the explosive birth of spacetime. But nestled within this primordial glow, astronomers have found something that shouldn't be there: eerie, concentric rings like ripples frozen in a pond. These circular patterns appear too perfect, too structured, to fit our standard models of cosmic evolution. Some theorists argue they could be echoes from before the Big Bang, ghostly imprints of events that unfolded when our universe was just one bubble among many in an unfathomable multiverse. One of the most striking examples is the so-called cold spot, a vast circular region in the CMB where temperatures dip lower than expected. At first glance, it might seem like just another cosmic quirk, but the odds of such a perfect, large-scale cold ring forming by chance are astronomically slim. This anomaly led physicists like Laura Mersini-Horton to propose a radical explanation. The rings might be collision scars from other universes bumping against ours in the distant past. Picture two soap bubbles brushing together in a sink. The point of contact would leave a circular mark on each. If our universe experienced such a collision, the energy released could have imprinted these rings into the fabric of spacetime itself, leaving traces we now see as temperature variations in the CMB. Not everyone is convinced. Skeptics point out that statistical anomalies exist in any large dataset, even the cosmic microwave background. They argue the rings could simply be flukes, artifacts of how we process the data, or the result of unknown astrophysical processes within our own universe. Others suggest more conventional explanations, like massive sound waves rippling through the early universe's plasma, leaving behind subtle circular signatures as they dissipated. The challenge is that the CMB is a snapshot of a single moment in time, frozen when the universe was just 380,000 years old. Untangling whether these patterns are echoes of a deeper reality or just cosmic static is like trying to reconstruct a symphony from a single note. Yet the implications are too profound to ignore. If these rings do trace back to pre-Big Bang events, they'd be our first glimpse beyond the birth of spacetime evidence that our universe is part of something far grander. Some models of eternal inflation, a theory suggesting the Big Bang was just one of countless expansions in an endless multiverse, predict exactly this kind of imprint. The rings could be cosmic breadcrumbs leading us toward answers about where we came from and what lies beyond the edges of our cosmic bubble. For now, the debate rages on. New telescopes like the Simons Observatory in Chile are scanning the CMB with unprecedented precision, searching for more of these enigmatic patterns. Whether they're statistical ghosts or multiversal fingerprints, one thing is certain: the universe is still whispering secrets from its earliest moments. And if we listen closely, we might just hear the echoes of realities beyond our own. Our universe stretches far beyond what any telescope can see, but just how far? The Hubble volume defines the ultimate frontier of observation, a sphere centered on Earth with a radius of about 93 billion light-years. This isn't just the limit of our technology, it's the limit of physics itself. Light from anything farther hasn't had enough time to reach us since the Big Bang, placing those regions forever out of view. It's like standing in a dense fog. You can only see so far before the mist swallows everything. But here's the twist: the universe might not end at that boundary. In fact, it could stretch infinitely beyond, leaving us forever trapped in our pocket of spacetime, wondering what lies in the unreachable dark. What makes the Hubble volume so humbling is its impermanence. Over time, the expansion of the universe pulls galaxies beyond this cosmic horizon, their light fading like distant ships disappearing over the edge of the world. Already, galaxies once visible to Hubble have vanished from sight, their light stretched into oblivion by the relentless growth of space. Future civilizations, if they arise billions of years from now, will peer into a far emptier sky, their Hubble volume contracted by the accelerating expansion of the cosmos. The window to the universe is closing, slowly but surely. Yet the most tantalizing question isn't about what we can see, it's about what we can't. If the universe is infinite, as many theories suggest, then beyond our Hubble volume lie countless other volumes, each with their own galaxies, planets, and perhaps even life. Some could mirror ours almost exactly, while others might obey entirely different physical laws. The catch: we'll never know. No signal, no matter how powerful, can traverse the gap between these regions fast enough to beat the expansion of space. They're not just distant, they're fundamentally severed from us, islands in an eternally widening sea. Some cosmologists argue this infinite expanse might even host copies of ourselves. In a universe without end, every possible configuration of matter repeats eventually. Somewhere out there, in a Hubble volume trillions of light-years away, an identical Earth might orbit an identical sun, with identical versions of us pondering the same questions. It's a dizzying thought, but also a lonely one. The very laws that make the cosmos vast and varied also condemn us to a solitary corner of it, forever guessing at what lies beyond the veil. The Hubble volume is both a gift and a prison. It grants us a glimpse of the universe's grand tapestry, but it also fences us in, teasing us with the knowledge that most of existence lies forever out of reach. Whether finite or infinite, the cosmos keeps its deepest secrets locked away, reminding us that some mysteries aren't just unsolved, they're unsolvable. And yet, that's what makes astronomy so thrilling. The universe isn't just a puzzle to be cracked, it's an endless story, most of which we'll never get to read. Beneath the smooth fabric of space and time we perceive lies a hidden chaos, a seething, turbulent froth known as quantum foam. At scales trillions of times smaller than an atom, space-time itself churns like a stormy ocean, bubbling with fleeting particles and microscopic wormholes that flicker in and out of existence too quickly for any detector to catch. This isn't just empty space, it's a realm where the very concepts of here and now break down, where gravity and quantum mechanics wage a silent war for dominance. The idea of quantum foam was born from a clash between two titans of physics: Einstein's general relativity, which describes the graceful curvature of space-time, and quantum mechanics, which governs the frenzied behavior of the subatomic world. When you try to merge these theories, space-time stops being a static stage. It becomes a dynamic, frothing mess at the tiniest scales. Imagine trying to measure the surface of a lake during a hurricane. Your measurements would fluctuate wildly because the water itself is in constant turmoil. Quantum foam is like that, but for the fabric of reality. Particles pop into existence, borrowing energy from the vacuum, only to vanish moments later, while space-time twists into knots so tight they could be bridges to other universes or just cosmic mirages. Why can't we see it? The problem comes down to scale and energy. To probe quantum foam directly, we'd need a particle accelerator the size of the Milky Way, capable of unleashing energies a quadrillion times more powerful than the Large Hadron Collider. Even if we could build such a machine, the foam's features last for mere fractions of a yoctosecond, a timescale so short it makes the blink of an eye seem eternal. It's like trying to photograph a hummingbird's wings with a camera that only snaps one picture a year. Yet indirect clues hint at foam's existence. Some physicists study high-energy cosmic rays, particles that streak across the universe at near light speed. If space-time is frothy, these rays should arrive slightly scrambled, their paths jostled by the microscopic bumps and twists along the way. Others look for subtle anomalies in the light from distant quasars, searching for signs that the foam has subtly distorted their journey over billions of light years. So far, the evidence is tantalizing but inconclusive, like catching whispers in a thunderstorm. The wildest implication: quantum foam might be the key to unlocking time travel or warp drives. If space-time can fluctuate so violently at tiny scales, could we somehow stabilize a bubble of it, creating a shortcut through the cosmos? The math suggests it's theoretically possible, but the energy required is beyond anything we can fathom. For now, quantum foam remains a frontier not of distance, but of scale, a reminder that the universe's greatest secrets aren't just in the stars above, but in the invisible, seething depths beneath our feet. Imagine throwing a book into a fire. You might lose the physical copy, but in theory, the information within it could be reconstructed from the ashes and smoke. Now picture that book as a particle falling into a black hole. According to Einstein's general relativity, that particle's information is gone forever, sucked into a singularity where the laws of physics break down. But quantum mechanics insists that information can never truly be destroyed. It might get scrambled, but it can't vanish without a trace. This contradiction is the black hole information paradox, a crisis at the heart of modern physics that's been raging since Stephen Hawking first proposed it in the 1970s. The conflict centers on Hawking radiation, the faint glow that black holes emit as they slowly evaporate. Hawking showed that black holes aren't entirely black, they leak particles over time, losing mass until they eventually vanish. The problem: that radiation appears to be completely random, carrying no trace of the information swallowed by the black hole. It's like burning a library and claiming the smoke contains no hints of the books inside. Quantum mechanics rebels against this idea. If information is lost, it violates the principle of unitarity, the bedrock rule that the past should always be theoretically reconstructible from the present. One radical solution emerged in 2012, the firewall paradox. Imagine the event horizon of a black hole not as a passive boundary, but a seething wall of high-energy particles, a cosmic kill zone that incinerates anything crossing it. This firewall would protect information by ensuring it never enters the black hole in the first place, instead encoding it into the radiation. But here's the catch: firewalls defy Einstein's equivalence principle, which states that free falling into a black hole should feel like floating in empty space, not plunging into an inferno. The debate exploded, with physicists divided over whether firewalls were a necessary fix or a sign that deeper physics was at play. Recent breakthroughs, however, are rewriting the script. The holographic principle, inspired by string theory, suggests that all the information inside a black hole might be encoded on its surface, like a three-dimensional movie stored on a two-dimensional disk. In this view, Hawking radiation isn't random but a complex cipher, preserving information in ways we're only beginning to decode. Simulations using quantum computers have even shown tentative evidence that information can escape black holes, scrambled but intact, hidden in the correlations between emitted particles. The most tantalizing development comes from wormholes, or more precisely, their quantum cousins, Einstein-Rosen bridges. In 2020, physicists discovered that entangled particles might be connected by microscopic tunnels through spacetime, offering a path for information to escape a black hole without violating any laws. It's a wild idea. Black holes could be cosmic shredders, not destroyers, leaving behind a trail of quantum breadcrumbs that, if pieced together, would reveal everything they ever consumed. What makes this paradox so electrifying isn't just the clash of theories, it's the stakes. Solving it could unify general relativity and quantum mechanics, bridging the last great gap in our understanding of reality. Whether the answer lies in firewalls, holograms, or wormholes, one thing is certain: black holes aren't just cosmic vacuum cleaners. They're the universe's most extreme laboratories, testing the limits of physics itself. And with every new insight, we're not just decoding the fate of information, we're rewriting the rules of existence. If the Hercules Corona Borealis Great Wall redefined our sense of scale, the Sloan Great Wall laughs in the face of cosmic modesty. Stretching over 1.4 billion light-years, this serpentine chain of galaxies is one of the largest known structures in the observable universe, so vast it would take a beam of light nearly twice the age of Earth just to traverse its length. Discovered in 2003 by the Sloan Digital Sky Survey, this wall isn't just a cluster or supercluster, it's a filament of the cosmic web, a thread in the tapestry of galaxies woven together by gravity's invisible hand. But what sets the Sloan Great Wall apart from its colossal cousin, the Hercules Corona Borealis structure, isn't just size, it's composition. While Hercules Corona Borealis revealed itself through gamma-ray bursts, the Sloan Wall is a gallery of galaxies, thousands of them strung along a filament like pearls on a necklace. Some regions are dense knots where galaxies crowd together, while others taper into lonely threads where only a few stragglers drift through the void. It's a snapshot of the universe's architecture at its most extreme, a blueprint of how matter organizes itself on scales almost too large to comprehend. Yet these walls share a deeper, more controversial trait. They both poke holes in one of cosmology's sacred principles, the cosmological principle. This idea, foundational to modern astronomy, states that on large enough scales, the universe should look roughly the same everywhere. No special places, no glaring outliers, but structures like Sloan and Hercules Corona Borealis defy that expectation. They're not just big, they're too big, stretching the definition of large enough scales to the breaking point. Imagine shaking a snow globe and watching the flakes settle into a perfect, mile-wide snowman. The odds of that happening by chance are absurd, just like the odds of these walls forming without some unseen hand guiding them. So what's really going on? One possibility is that these walls are illusions of perspective, chance alignments of smaller structures that only look connected from our vantage point. Like seeing a constellation in the stars, their apparent unity might be a trick of the light, but the math isn't so easily dismissed. Simulations show that even accounting for observational bias, the Sloan Wall's sheer coherence is hard to explain without invoking something extraordinary. Perhaps primordial density fluctuations from the Big Bang that were far more pronounced than we thought, or exotic physics like dark energy's uneven influence sculpting the cosmos in ways we don't yet understand. Then there's the unsettling implication that these walls might not be the exceptions but the rule. Recent sky surveys suggest the universe is peppered with similar, if smaller, filaments, all weaving through the voids like rivers cutting through a desert. If that's true, the cosmological principle might not be wrong, just incomplete. The universe could be homogeneous on average, but with wrinkles so vast they fool us into thinking we're seeing the whole fabric when we're only tracing a single thread. The Sloan Great Wall isn't just a curiosity, it's a challenge. A reminder that the universe resists easy categorization, and that every time we think we've grasped its structure, it reveals another layer of complexity. Whether these colossal filaments are cosmic accidents or clues to a deeper order, they force us to rethink the very framework of modern cosmology, and until we solve their riddle, they stand as monuments to the greatest truth of all. The universe is always stranger than we imagine. The cosmic microwave background should be the ultimate equalizer, a nearly uniform sea of ancient light left over from the Big Bang, with tiny temperature fluctuations scattered randomly like static on a television screen. But in 2003, astronomers poring over data from the WMAP satellite stumbled upon something that sent shockwaves through cosmology, a bizarre, unexpected pattern nicknamed the Axis of Evil. This wasn't just another anomaly, it was an eerie alignment of hot and cold spots stretching across the sky like a cosmic equator, as if the universe itself had picked a favorite direction. What makes this axis so unsettling is how thoroughly it defies expectations. According to the standard cosmological model, the early universe was a chaotic, seething mess, with quantum fluctuations creating random density variations that later grew into galaxies and clusters. There should be no preferred direction, no up or down to the cosmos, just an even distribution of irregularities. Yet the axis of evil suggests structure where none should exist, like finding a hidden arrow painted across the night sky, pointing toward some unseen significance. The name itself reflects the discomfort it caused. Labeling it evil was a tongue-in-cheek nod to how thoroughly it upended assumptions. Theories attempting to explain it range from the tantalizing to the unnerving. Some suggest it could be a statistical fluke, an illusion created by how we process the data. After all, with trillions of potential patterns in the cosmic microwave background, one odd alignment is bound to appear purely by chance. Others propose more exotic explanations, like the gravitational influence of a neighboring universe tugging at ours from beyond the cosmic horizon, imprinting a directional bias we can't otherwise detect. There's even speculation that dark energy, the mysterious force accelerating the universe's expansion, might not be uniform but aligned along this axis, warping space-time in subtle ways we're only beginning to perceive. Then there's the most controversial possibility that the axis hints at a fundamental breakdown in our understanding of the Big Bang. If the universe does have a preferred direction, it could mean the initial conditions of creation weren't as symmetric as we thought. Perhaps inflation, the rapid expansion moments after the Big Bang, didn't happen uniformly, leaving behind wrinkles in space-time that now manifest as this strange alignment. Critics argue this would undermine the very foundation of modern cosmology, forcing us to reconsider ideas we've held as gospel for decades. Yet for all the debate, the axis of evil refuses to vanish. Subsequent observations, including data from the Planck satellite, have both confirmed and complicated the picture. Some features of the alignment persist, while others fade under closer scrutiny. It's as if the cosmos is teasing us, offering glimpses of something profound before slipping back into ambiguity. Whether a flaw in our models, a glimpse of deeper physics, or just cosmic noise, this mysterious axis stands as a reminder that the universe rarely fits neatly into our boxes. And until we crack its code, it remains one of cosmology's most tantalizing loose threads. A whisper that the story of creation might be stranger than we ever imagined. But what if our universe isn't alone? What if it's just one page in an infinite cosmic library shelved among countless others, each with its own laws, its own history, its own version of reality? This is the tantalizing promise of the multiverse, a hypothesis that stretches the imagination to its limits. While we can't observe these alternate universes directly, they lie forever beyond the horizon of our Hubble volume. Their potential existence isn't just science fiction. It's a serious frontier of physics, one that emerges naturally from the math of inflation, string theory, and quantum mechanics. Picture a bubble bath where each bubble is a self-contained universe, inflating in its own direction, governed by its own unique constants. In some, gravity might be stronger, snuffing out stars before planets can form. In others, the fundamental forces could be so weak that matter never clumps together at all. A rare few might resemble ours, with just the right conditions for galaxies, life, and curious minds to ponder their place in the cosmic froth, the unsettling truth. We'll never visit these realms or even glimpse them. The space between universes isn't just vast, it's expanding faster than light can cross it, erasing any hope of contact. So why believe in something we can't see? The answer lies in the math. Eternal inflation, a leading theory of the Big Bang, suggests our universe's explosive birth wasn't a one-time event but an endless chain reaction, spawning pocket universes ad infinitum. String theory takes it further, proposing a landscape of possible universes, each a different solution to the equations, like tuning a radio to endless stations, most playing static, a few crackling with coherent sound. Even quantum mechanics hints at parallel realities through the many worlds interpretation, where every decision branches space-time into new timelines. Yet the ultimate irony is that these universes aren't just hidden, they're fundamentally hidden. No telescope, no matter how advanced, could peer beyond our cosmic horizon. The space between universes isn't empty vacuum. It's a seething, metastable energy field stretching endlessly, a barrier no signal can breach. Any light from another universe would be redshifted into oblivion before it reached us, its message lost in the noise of expansion. But here's the twist: absence of evidence isn't evidence of absence. The multiverse might leave fingerprints in our own reality. Some theorists hunt for cosmic bruises in the CMB circular patterns like the cold spot, possibly caused by collisions with other universes in the distant past. Others suggest dark energy's mysterious strength could be a side effect of neighboring universes tugging on ours through higher dimensions. Even the unsettling smoothness of our universe's initial conditions might make sense if inflation cherry-picked our bubble from an infinite ensemble. The multiverse isn't just a flight of fancy, it's a mirror held up to the limits of human knowledge. It forces us to confront the possibility that some truths might lie forever beyond reach, not because we lack ingenuity, but because the cosmos itself has built the walls too high. Yet in that vast, invisible ensemble of realities, there's a strange comfort. If every possible universe exists, then somewhere out there, in a realm we'll never see, every lost chance, every road not taken, every alternate history unfolds in parallel. It's a reminder that the universe, in all its mystery, might be far grander than we ever dared to dream. From the gravitational siren song of the Great Attractor to the ghostly whispers of the wow signal, these 25 enigmatic regions of the universe remind us just how much lies beyond our grasp. We've wandered through cosmic deserts like the Boötes Void, marveled at the impossible scale of the Hercules Corona Borealis Great Wall, and stood at the precipice of black holes where information itself seems to vanish. Each one defies expectations, challenges our theories, and humbles us with the realization that the cosmos is far stranger, far grander than we ever imagined. But here's the beautiful truth: these mysteries aren't dead ends, they're invitations. Every unanswered question, every anomalous data point is a breadcrumb leading us deeper into the unknown. Think of the pioneers who first mapped the stars with nothing but naked eyes and curiosity. They couldn't have dreamed of Hubble's deep field images or the Event Horizon Telescope's glimpse of a black hole's shadow. Yet their questions laid the groundwork for the discoveries that astonish us today. What will the next century reveal? Perhaps we'll decode the dark flow's secret, proof of realities beyond our cosmic horizon. Maybe we'll catch another signal, deliberate and unmistakable, rewriting humanity's place in the universe. Or perhaps the biggest revelation will be something we haven't even thought to ask yet. The one constant in astronomy is surprise. Every time we think we've glimpsed the universe's full story, it whispers, "Wait, there's more, so stay curious." Look up at the night sky and remember, those glittering points are just the prologue. Behind them lie voids we can't cross, forces we can't see, and questions we can't yet answer. But with every telescope we build, every equation we refine, we're chipping away at the unknown. The universe isn't just a place, it's a conversation, one we've only just begun. And the next chapter, it's waiting for you to wonder.